Hi, my name is Bruce Ravel. I'm a physicist in the Materials Measurement Laboratory at NIST, the National Institute of Standards and Technology. And I'm also the lead beamline scientist at the Beamline for Materials Measurements here at the National Synchrotron Light Source 2. Today I'm going to talk to you about a problem where we use X-rays to address an issue of art curation and cultural heritage. The amazing place that you see on the screen right now is Bangkok's Grand Palace. It's an official residence of the Thai royal family, and it's also the site of the famous Temple of the Emerald Buddha. And the thing I'm actually going to talk about is not the interior of the temple, but how the exterior of the temple is decorated. What you see here is a pillar on the outside of the Temple of the Emerald Buddha, and it's showing a thing that in the 1830s was an important artistic development in the region. So this temple was built in the late 1700s and renovated in the 1830s to become the home of the Emerald Buddha. The walls and exterior pillars, like you see here, were decorated with glass mosaics. This was an innovation. Prior to the 1830s, temples of this sort were decorated in a different way. And today, you can see temples all over the region that have glass mosaics as the exterior decor. Here's a closer picture of the glass mosaic that you saw in the previous picture of that pillar. And you see that the original glass has a certain characteristic look. It's obviously handcrafted. It's obviously antique. It has a certain appearance to it, a certain beautiful appearance. The way that these glass mosaics were made is that the small pieces of colored glass were cut into shape and covered on one side with metal to turn them into little mirrored pieces, and then they were glued to the wall or to the pillar using natural latex, using rubber. Over time, the rubber has degraded and pieces of glass have started falling off of the wall at the temple over the decades. In recent decades, these mosaics have been restored using modern factory-produced glass. These are still really beautiful objects, really beautiful mosaics, but the appearance is different. The modern glass is more uniform in color, more uniform in texture, and just has a very different appearance. So the question that my scientific colleagues in Thailand were asked is if it was possible to recreate these older glasses using the original methods of glass production. This is a really interesting question and could lead to a new form of renovation of these mosaics. But first, we're scientists, and to begin this project, we have to understand what the composition of the glass is. So here's another picture of another piece of a similar mosaic. And you see an example of the 5 different colors that are represented in these mosaics. The blue, yellow, green, and clear glasses are all very well understood using just very well understood features of glass chemistry. For example, the yellow and clear glass are very similar compositionally. They have the same stuff in them. They're glass that was made pretty much the same way, except that the yellow glass has more iron. And it's the presence of this additional iron that turns the glass yellow. The blue and green glasses can be understood in similar ways by just different amounts of iron, manganese, and other common elements that were introduced into the glass. But the red glass is different, and so what I'm talking about in this talk is what makes the red glass red. Well, to begin to understand a problem like this at the synchrotron, we use a measurement technique called X-ray fluorescence spectroscopy. And so here you see in the inset a couple of pieces of the glass from the 1830s that I brought to the beamline at the synchrotron and exposed to the X-rays. And the X-ray fluorescence spectrum that I'm showing you begins to tell us what elements are present in the sample. The peaks that are on the left side of the plot tell us that there's manganese and iron and copper, very common things in the glass. The interesting piece is that very tiny peak in the middle that I have labeled as gold. So why is gold interesting? Well, to explain that, I need to show you another piece of red glass. This object is called the Lycurgus cup. It is in the British Museum in London. And it's a very famous example from the late Roman Empire of what's called struck gold or ruby gold glass. And this object, this style of glass from that time period is very well understood, and it's been demonstrated that the red coloration is due to the presence of nanoscale gold particles, little tiny pieces of metallic gold that are dispersed throughout the glass. And so the question then is, are these glasses from the 1830s in Thailand a similar kind of glass? Are they also struck gold glass? Well, to begin to answer that question, we did another synchrotron measurement technique, a thing that's called X-ray absorption spectroscopy. It's the thing that's done at my beamline at the NSLS-II and is one of the core measurement techniques that we do at the synchrotron. What I'm showing you on the right are XAS spectra of various different forms of gold. The blue trace is metallic gold, and then the other four are just gold in different forms. And the thing that I want you to take away from this plot is that when you measure XFs on something, different things look different. So if you see one of these spectra in an unknown sample, well, then you know what the form of the gold is in that sample. So let me show you how that worked out for the glass. This turned out to be a rather difficult measurement because there's a very small amount of gold in the glass, and there were some other experimental difficulties that led to rather noisy data, as I show you on the bottom in the blue. But this spectra that we measured on the Thai glass is clearly the same thing as the gold foil, which is the red plot. They overplot almost exactly, so we have demonstrated that the gold in the glass is metallic gold. Okay, that's very interesting, but it leaves a couple of questions. Why does metallic gold make the glass red? And is the gold nanoscale? Well, to understand that, we did a third synchrotron measurement technique, this time using visible light. What I'm showing you here is optical spectroscopy. In short, this measurement tells us how the red glass absorbs the different colors of visible light. And you can see that features of the glass here, well, the way to understand this plot is that higher up on the scale of the plot means that the glass is more absorbing. And so you see that as you go from the blue into the violet and off into the ultraviolet, that the glass becomes very absorbing. So all of those colors are absorbed by the glass and do not make it to your eye. There's a peak in the middle that overplots the green part of the spectrum, and that peak takes the green light out of the light that's coming off of the glass. And so the only thing that makes it to your eye is the red. Because all of the other colors are absorbed by the glass appears to your eye to be red. Now, what's very interesting about that peak in the green is that we can understand that using knowledge of the physics of how light and materials interact, and we can show that that bump in the green is due to the presence of 30 nanometer gold particles dispersed in the glass. So without the gold, the green light would make it through the glass into your eye, but with the gold, the green light gets taken away and it's only red. It might be a bold claim to say that without the gold particles, this red glass would look green. That might be a bold statement, except that I can show you that. Here are a couple of examples of glass that were made by my Thai colleagues using the exact same formulation, one as the other, and the same formulation as the red glass from the 1830s, with the exception that the one on the left has no gold added to it, and it's green. We put some gold in the glass, and the gold absorbs the green light and leaves only the red light to make it to your eye. So the moral of this story is that in the 1830s, the Thai glass craftsmen were nano-engineers. So science is never done by one person, and this was not all done by me. I need to acknowledge my two collaborators. On the left is my friend and colleague Wantana Kleisaban, who is the lead scientist at a beamline at the synchrotron in Thailand. Wantana introduced me to this really interesting problem and took me to see the surviving original mosaics in Bangkok. Larry Carr is a colleague of mine here at NSLS-II, and Larry's involvement in this project is a testament to the importance of the hallway encounter. There was a day that I ran into him, and he asked me what I was working on, and I said, well, I have this interesting problem that you might know something about. And sure enough, he did, and that led to the work that we did on the optical spectroscopy and the demonstration that the gold actually is in the form of nanoparticles in the glass. So to close this out, I want to show you what my Thai colleagues have done in terms of the original problem of being able to restore the original glasses. On the left, what you see are side by side in 3 different colors, examples of the original glass from the 1830s with modern recreations in Wantana's laboratory. And you see that they've done a really good job of reproducing the coloration and texture of the original glasses. The picture on the top on the right is a small decorative stained glass object that they created using the modern recreations of these glasses. On the bottom, you see my friend Wantana presenting that small glass window to Princess Shittenhorn, who is the sister of the current king of Thailand. So this was my story about using synchrotron radiation, using X-rays to understand something about art curation and cultural heritage. Thank you very much for listening.